In this video I talk about constrained minimization of a function. The video is based on the example script example_min_con. I will skip over the usual preamble. You know it already from previous videos, so I go directly to line 15, which is the definition of the function handle. Let me now create a contour plot. I will skip over the entire code that creates a contour plot. This is very similar to the ones in my previous videos. And let me go directly to line 44, where we start with the minimization. So I start by setting some options. I have set the display to none. We can change that and get some more display. Let me set the display to iter, which means information for every iteration of the solver. I set some functions. I demonstrate the solver, which is called fmin_con, on four different examples with linear inequalities, linear equalities, and non-linear equality. In addition, we can also switch on some bounds for the minimizer. Okay, let me step to my first example, which is a linear inequality of x and y, which means the minimum of the function is confined to a half plane defined by a line with the equation y equals 2x minus 1. If we look at the minimizer fmin_con in more detail, we see that it has a lot of different calling sequences. Let me maximize the help window. Okay, here we are. So this is the documentation for fmin_con. So let me explain how you specify the constraints in the minimizer, in the call to the minimizer. The simplest one is the one we are looking at in the first example, a linear inequality of the form a times x is less or equal than b. X in our case is the coordinate vector, which consists of x and y, or x1 and x2. A is a matrix, and b is a scalar. So we have to reformulate the constraint such then that it is expressed in the form a times x less or equal to b. The calling sequence of fmin_con is similar to the one of fmin_nunc. The first argument is the function handle. The second argument is the starting value, the starting point. And then there is a list of constraints. In our first example, the list is just a and b expressing an inequality constraint. Now let's see how we reformulate the constraint so that it has the prescribed form a times x less equal to b. So we return to the editor window. So the linear inequality reads a is larger or equal to 2x minus 1. So we have to reformulate this in the following way. Please have a look at line 51. Y greater equal 2x minus 1 means 2x minus y is less or equal to 1. If we divide by 2, we get x minus y over 2 is less equal 1/2. We can write this in matrix vector form in the following way. The matrix A is 1 and minus 1/2, and the constant B is 1/2. So A times the vector x, y transposed is less or equal than 0.5. This gives us the matrix A and the constant B. So A and B are set in lines 53 and 54. We choose a starting point somewhere, doesn't matter where, probably. The function is not very complicated. You can see that it has a saddle point around minus 0.5 and minus 1. And if you go north and south, the function rises. If you go east or west, the function drops. So the structure is not overly complicated, and the starting point should not have much influence on the result. So how do we now call the minimizer? Well, it's called fmin_cont. The first argument is the function handle, as I said before. The second one is the starting point. Argument 3 and 4 are A and B. And as we want to use options, we have to put empty arguments in all the places before the last argument, which is the options. The output is similar to fmin_unc, even identical. It's the point of the minimum, xmin. It's the function value at the found constraint minimum, the exit flag, which should be not 0, and output structure. Lam, this is different from fmin_unc. Lam is the vector of Lagrange multipliers, which are used during minimization. And then we have the gradient and the Hessian. Okay, let's try to call the minimizer. You see in the command window the display for every iteration. You see the function value in the third column, and you see that it drops and then stabilizes at around minus 1.776. So this is the minimum of the function under the constraint that we have defined by the matrices A and B. Now let's look at the graphical representation of the solution. With a linear constraint, so the half plane where the solution has to be is bounded by a line. You see the line in light blue. This is the boundary of the half plane where the solution has to be. We can also plot the solution itself and the contour line through the solution point. At the point of solution, the contour line must be parallel to the line that bounds the half plane. in fact, the solution is confined to the half plane to the upper left of the boundary line, and the solution is the point with the smallest function value in this half plane. Let us step to the second example. I've put a keyboard command in 115, so we can continue from here by the command db step. And we go to our second example, which is a linear equality. This means a solution has to lie on the line defined by y equals minus 3x minus 2. Again, we have to reformulate the equation of this line such that it can be written in the form a times x, the coordinate vector, equals minus 2. Well, that's not very difficult. We can reformulate the equation as shown in line 60. So if y equals minus 3x minus 2, then 3x plus y equals minus 2, or the matrix or the row vector 3, 1 times the column vector xy equals minus 2. So A equals 3, 1, the row vector 3, 1, and B equals minus 2. We choose a different starting point somewhere in the rectangle. Now we have to provide arguments 5 and 6 to fmin_con. 3 and 4 are reserved for linear inequalities, and A and positions 5 and 6, A and B in position 5 and 6, they indicate a linear equality. So let me step to the graphical representation. Here we see the solution, and let me step directly to line 115. And on the right hand side in figure 1, we now see the second line in dark blue. The solution has to be on this line, and the solution is a point where the function value of our function along this line is minimal. Again, I've also drawn the contour line through this point, and you can see that the contour line is parallel to the constraint line at the point of solution. Let's step to our next example, the third one, which is a linear equality with additional boundaries. The linear equality constraint reads y equals minus x minus 1. And the boundary conditions are x must not exceed 0 and y is larger or equal to 0. So we have boundaries both in x and in y. The reformulation of the equality constraint is straightforward again. We have y equals minus x minus 1. From this follows x plus y equals minus 1. So A, the matrix A, is the row vector 1, 1, and the constant B is minus 1. Another starting point, and now we have to define the boundaries. These are the arguments 7 and 8 to fmin_con. Each of those is a vector of 2 values in this case, specifying the lower boundary for x and y, So the lower boundary for, let's look in line 74, the lower boundary in x is minus infinity and the upper boundary is 0. In line 75 we have the upper boundaries which are 0 for x and infinity for y. Let's again call the solver now with both the equality constraints in the matrix A and the constant B in position 5 and 6, and then the lower and the upper boundary in positions 7 and 8. Unused inputs have to be provided as empty arrays. The linear equality constraint is now represented by the black line, and the solution is constrained to a quadrant which is x must be negative and y must be non-negative. And the solution is shown in figure 1 in black. I've also drawn the contour line which is parallel to the constraint line in the point of solution at the constraint minimum, constrained by the linear equality and constraint to the quadrant x negative, y non-negative. We have one more example, which is now a nonlinear constraint, a nonlinear inequality constraint. In addition, we also have bounds. The solution is confined to the first quadrant, x and y non-negative. A nonlinear constraint has to be represented by a function handle, and this is done in line 82. So this is the constraint on the two coordinates x1 and x2. You can see it's a circle with radius 1/2. We define a starting point. We define the boundaries for x and y. In this case, the lower boundaries are 0, both for x and y, and the upper boundaries are infinity for both x and y. Now, how do we pass the constraint to fmin_con? Well, in the last but one argument, we have to specify a function handle. In this case, I've called the function nlcon, and now let's have a look at the function nlcon. Its arguments are the position x, so x and y, and the constraint, which is a function handle. Now, what does this function look like? The function has, as you can see, two input arguments, x, the position and the constraint, and it has two output arguments, which are called c and c_ec. In c, you can specify inequality constraint, and in c_ec, you can specify the equality constraint. Let's put a breakpoint here and see what is done in this function if we call the minimizer. We are now inside the constraint function. We see the position in the input argument x. This is a starting value at 1.5 and 0.5. Now, let's have a look at the constraint. This is the symbolic constant cons. It's a symbolic constant which depends on x1 and x2. So we look which are the variables in the constraint, and we substitute x1 for capital X1 and x2 for capital X2. Why? Because x, the input x, is a vector of 2 coordinates. Now we set C equals to the empty vector, which means there are no inequality constraints. And Cx is now the equality constraint, which is just the value of the constraint at the given input point x. So the constraint is evaluated at the position x, which is given to the function. And that's it. We can step outside the function. By the way, I forgot to mention that we want to maximize, not minimize, but maximize with this nonlinear equality constraint. So the first input f min con is a negative of the function, and after the maximum has been found, we have to reverse the sign of the function value, because the result in fy is the function value at the maximum of the negative of the function. So let's clear this breakpoint, because nlcon is called many times. It's called, of course, in every iteration that the minimizer has to do. And let's go directly to line 115. The nonlinear constraint is plotted in red. It's a red circle, which you can see in figure 1. You can see the constraint maximum of the function constrained to the circle. In addition, the solution is constrained to the first quadrant. X and y must not be negative. So x and y have to be non-negative. In the legend, you can see the exact positions of the constraint minima, and the last one, the constraint maximum, which is drawn in red. At the maximum, the contour line has to be parallel to the circle.